Good morning, friends. We are now with the new topics about Ampere's circuital law. We have completed Biot-Savart's law and its application. Now we are dealing with what? Ampere's circuital law. What does it state? It states that the line integral of magnetic field around any closed path is mu naught times of the total current flowing through the circuit. Suppose the current I is flowing through it, then magnetic field around it will be mu naught times, that means permittivity times of the total current flowing through the conductor. Is it clear? It is same if you go through the Gauss theorem. What with Gauss theorem it states the total flux. There was a in Gauss theorem there the total flux is equal to what? 1 by epsilon naught times of the total charge. Here total magnetic field is equal to what? Mu naught times of the total current flowing through the circuit. Mathematically it will be how much? Closed integral of B vector dot dl vector equal to mu naught I. To prove it, let us take a conductor through which current infinitely long straight wave conductor is there, through which current I is flowing. And we know that if the current is going in this way, the magnetic field around it will be in the form of concentric circle. Let us take one such circle having radius r. Okay, and we have assumed that it is at a point, it is from the circle. A point is there where we have assumed a length element dl is there. Now we know that for an infinitely long straight wave conductor, B equal to mu naught I divided by twice pi r. Here or not? If we, as we have taken dl as the length element, then you can say closed integral of B vector dot dl vector equal to closed integral of B dl cos 0 degree equal to B closed integral of dl equal to B into 2 pi r, which means equal to mu naught I divided by 2 pi r into 2 pi r equal to mu naught I, which proves our Ampere circuital law. Again I am repeating, we have taken a conductor through which current, infinitely long straight wave conductor through which current I is flowing, and the magnetic field around it will be in the form of concentric circle. Let us take one such circle having radius r. Then magnetic field on the circumference of the circle will be how much? B equal to mu naught I divided by twice pi r. And we have assumed dl is the length element on this circle. Then closed integral of B vector dot dl vector equal to B dl cos 0 degree equal to B closed integral of dl equal to B into 2 pi r equal to mu naught I divided by 2 pi r into 2 pi r will get what? Mu naught I. So that is about your magnetic, what we can say, Ampere circuital law. Now we are going to find out the applications of this Ampere circuital law. Okay, friends, before starting another application, I want to tell you about the limitation of Ampere circuital law. One important limitation is that it cannot find out the magnetic field intensity due to a circular coil carrying current. Why it cannot find out? At the center it cannot find out. Because why? We have to consider the length element. Okay. But when you are going to find out in magnetic field with a circular coil carrying current, the magnetic field will be where? At the center. Okay, if you are going to find out center, we cannot consider what is the length element. So it has a limitation that what it cannot be used for finding out the magnetic field due to a what? Circular coil carrying current. Here we are going to find out the magnetic field due to an infinitely long straight wire conductor. Our first application is magnetic intensity due to an infinitely long straight wire conductor by using Ampere's circuital law. We have already find out by using what? Biot-Savart's law. It was a tough topic was there, but what is there? If it is asked in the examination, you have to write. If it is mentioned that you find out this magnetic field with a long straight wave conductor by using Ampere's circuital law, then only you are allowed to do this one. Is it clear? How can we do? We have considered an infinitely long straight wave conductor through which current I is flowing, and the magnetic field around it will be in the form of concentric circle. Magnetic field will be in the form of concentric circle. Is it clear? Let us take a length element dl here. Then according to Ampere's circuital law, what we can say, closed integral of B vector dot dl vector equal to mu naught into 1. Implies what? Closed integral of B dl cos 0 degree, because magnetic field and length element are in the same line, so their angle is what 0 degree is equal to mu naught into I. So it implies what B in closed integral of B are equal to mu naught into I. Implies B into 2 pi R is equal to mu naught into I. It implies what? B equal to mu naught I divided by 2 pi R. Clear or not? So that is about your Ampere circuital flow. First application, what is magnetic field intensity due to infinitely long straight wire conductor. And the next application is what? How can you find out the magnetic field due to a solenoid? And how can you find out the magnetic field due to a toroid? There are two applications that I will discuss it. Wait. Now we are going to find out magnetic field intensity due to a solenoid. Magnetic field intensity due to a solenoid. First of all, we should know what is solenoid. Suppose this is a conductor, okay, and we tied it with the help of what? With a wire, okay. And if we tied it and take it out, and if we give the magnetic field around it, if we take a spring also, if we take an example of spring, if you give current through it, then what will happen? Magnetic field will be around it, inside the solenoid, it's maximum, and outside the solenoid is far away from it. But here, near the conductor, it is what? Magnetic field is 0. So to find out the magnetic field intensity due to a solenoid, let us take a conductor having n number of turns per unit length. Look what we have done. We have taken n number of turns per unit length. Okay, now we are going to find out, that magnetic field intensity due to a solenoid. For that, we have considered a solenoid is there having small n number of turns per unit length. How many turns? There are small n number of turns per unit length. And we have assumed that I equal to current flowing per unit turn. Then, if n equal to total number of turns, then capital N equal to how much? Small n into M. And total current will be how much? Small n and I. Now, to find out the magnetic field intensity, let us assume an Ampere loop. It will be same as what? As we have taken Gaussian surface. Here we have taken Ampere loop. And as it is in the form of what? Rectangle, so we have taken also a rectangular circle. Okay. So this is what A, B, C, D, whose length is same as the conductor. That means for solenoid, its length is L total. So we use the Ampere circuital law where when you use closed integral of B vector dot dl vector equal to mu naught into total current flowing through the solenoid. Is it clear? Now if you start it from A to B, what we can say? A to B, B vector dot dl. Then B to C, we can say open integral when you are going to start it. B to C, B vector dot dl vector. Now C to D, B vector dot dl vector. Then D to A, B vector dot dl vector. Equal to how much? Mu naught n L I. Is it clear? So here you will see that they are in the same line. So B dl cos 0 degree. Here it will be perpendicular. So B dl cos 90 degree. Here outside it is 0. Here it will be again 90 degree. So cos 90 degree is 0, but cos 0 degree is 1. So we come to say that outside it is 0 because 90 degree is very far away. Near the conductor is 0. So we can say that B dl cos 0 degree will be alive and others will be 0. So it will be equal to mu naught and alive. Now if we convert B closed integral of dl. Integral of dl is what? Total L. So B into L equal to mu naught and Li. Is it clear? M equal to mu naught and Li. So if L will cancel out, you will get what? B equal to mu naught and I. So it implies that B equal to mu naught n by L into I. So this is about your magnetic field due to a solenoid. Is it clear? Friends, our next topic is what? Magnetic field intensity due to a toroid. Toroid is what? Suppose if you have taken a tube of a tube, not cube, tube. There is that when the car is running, cycle is running, you know that we always run with what we inside the tire there is a tube in there. Suppose if you have taken a tube of a truck and you tie it by some what? By wire. Let us take the example of given some examples in the advertisement also is there. Ad is given in the TV every day. We know that, but some ad is given. If we आप उसको जला दो तब भी वो वायर नहीं जलता है, ट्यूब को जला दो. So you have taken a tire and you tied it by a wire. Okay, and when you tie it and you do one thing, you have done the tire, you have given some current here. What will happen? The magnetic field here it will be zero, and outside it will also be zero. But maximum magnetic field inside inside this tube area. Okay, in the form of circle. So let us take one such circle having radius r, and we have assumed that the current is there are n number of turns per unit length through which current I is flowing. Current I is flowing per unit terms. In unit terms, current I is flowing. And total number of turns, if it is capital N, then what will be the total N? Capital N equal to small n into twice pi r, because we have taken the radius as small r. The total current is equal to what? N into 2 pi r into I, because we have told that earlier. I is the current flowing per unit turn. Now, according to Ampere's circuital law, we have taken a small circle whose radius is r and small length element is there, whose length element is dl. So we can say that closed integral of B vector dot dl vector equal to how much? Mu naught into total current flowing to the toroid. Okay, flowing to the toroid. So it is how much? B into dl cos 0 degree, because B and dl are in the form of circle. B and dl in the same side. So we can say that what? Their angle is 0 degree. So it will be how much? B into dl cos 0 degree mu naught n into 2 pi r into I. So if you taken out dl, we can say B closed integral of dl mu naught n into 2 pi r into I. Implies B into 2 pi r equal to mu naught n 2 pi r into I. Implies B equal to how much? Mu naught n I. Implies B equal to how much? Mu naught n by 2 pi r into I. So this is about your magnetic field intensity due to a toroid. Is it clear? So I think applications are little bit over. However, you have to go through the whole chapter, and then we will discuss with the new topics. Okay, thank you.